in the literature, as everybody is familiar here, there are either metric perturbations or curvature perturbations. And if we imagine for a moment the simplest situation of a Schwarzschild black hole, in the metric perturbation case, the mostly developed formalism is the so-called Regel-Wheeler and Zerilli formalism. Whereas, for what concerns curvature perturbations, we face with the so-called Fiogorski formalism, Fiogorski equation. And let me say that this second approach can be further generalized not only in the stationary and symmetric case of Hadley, but for more general tightly spacetimes. So I'm mostly interested in the first case because I would like to elucidate the main difficulties to arrive at fully analytical new results. The resolution of the perturbed metric in the Schwarzschild space. It's better to say, since now what will be the end? We will perturb by some particle which is moving along a geodesic background spacetime, and in the end, the equations of the perturbation reduce to a single ordinary differential equation, which can be analytically solved now. More precisely, I'm interested in studying perturbations induced by test particle, also a gyroscope, but a test particle in this specific example, moving on the equatorial plane of the Schwarzschild black hole and along a circular line, which is a big simplification, but removing some of this special assumption is purely technical and does not require any other special information. Since 2013, we are now analytical or semi-analytical results available in post-Newtonian sense, whereas numerical studies and solution have been obtained even before. There is a common framework for this, and the new terminology is what is called gravitational self-force. This is nothing else the fact that the motion of the particle which is perturbing the spacetime can be read in the background spacetime, the Schwarzschild spacetime, but moving under the effect of its own self-force. So we say black hole perturbation or gravitational self-force problem, and these terminology are more or less equivalent. So a small mass, a small spinning body is moving on the equatorial plane of black hole space-time, produces a perturbation. This can be regularized somehow and fully analytically computed. There is a market where we can sell this result immediately, and the market is the effective one-body formalism, who was invented in 1999 by Alessandra Bonanno and Thibaut Moore. And this effective one-body formalism is capable to gather information coming from different contexts, like post-Minkowskian, post-Newtonian, and gravitational self-force or self-torque perturbation, as I'm going to discuss. And in the past few years, we have seen a lot of synergies because the conversion, any new results that's appearing in post-Newtonian can be immediately converted in AOB, and vice versa. For the first time, something has been computed first in EOB and then converted in other contexts. So we aim at the full reconstruction of the gravitational perturbations. This means, roughly, we will decompose the perturbation in multipoles, and then we have to take into account each of these movements in order to resolve the perturbation. As I told you, there is a big simplification working on perturbation induced by particles moving on a circular geodesic, because on the background the particles for velocity is a quasi-Keeling vector. But recent results have involved also always on the plane particles moving along eccentric orbits in Schwarzschild and in Kerr. In Kerr, the situation is a bit more complex, and we have not still obtained the same analytical results which are available now in Schwarzschild in the Kerr case. We can only give some detail, but the skeleton of the approach is shown in this slide. So first of all, the source. The source is a test particle. It has its own energy momentum tensor, which is a typical Dirac delta function located at the position of the particle, which evolves itself. The source should be given at the right-hand side of the Einstein equation, and then one has to solve the Einstein write down, and then solve the Einstein's equation in linearizing in the perturbation. So in the mass ratio of the particle, M1, and the black hole, M2. M2 is larger than M1. It's the black hole mass. So this term is a small correction to the background method. And this is the best we can first over in H. Okay? Then we expand the linearized Einstein equation in spherical harmonics, dealing with the Schwarzschild context. Then we split this equation according to the parity. There are even parity equations and odd parity equations, which should be solved differently. But in this way, we have removed the angular dependence on of the perturbation. So the theta and phi part of the perturbation is absorbed by the expansion in spherical harmonics, as we know. So we remain with the number of 10 partial differential equations involving only time and the radial line. Then we transform in Fourier transform in time, and the set of equations becomes ordinary. Still 10, still couple. The 70s already gave a lot of information on how to deal with this simplified situation. And the fact is that the odd parity equations can be reduced to a single ordinary differential equation, and this is called the Regge-Wheeler equation. The same is true for the even parity equations, which are now 7 and coupled. And these are summarized in a single ordinary differential equation, which bears the name of the Zerilli equation. Then Chandra came and showed that the Zerilli equation can be mapped into the Regge-Wheeler equation too, with different source terms. But the homogeneous part is exactly the same. So the problem is to solve analytically, in some sense, which I will show you in positive non sense, a single ordinary differential equation with the Dirac delta source term at the right-hand side. But we are going to solve this equation with the green function method. So what really matters are the solution of the homogeneous equation, which is the same in both cases. And this is a big simplification. Of this equation, which we can give to any mathematician, one can provide a number of solutions. The most interesting and the most simple one are post-Newtonian solutions, expanding the equations and then the solution in post-Newtonian sense in a way in which I will show in a moment. But post-Newtonian does not know the horizon of the Earth since the beginning. It will build the horizon by adding corrections. Okay? So at a certain point, post-Newtonian solution, if we want to obtain a very high post-Newtonian solution, cannot be used. And the Japanese school has provided a set of solutions which are regular both to the horizon and to the infinity. These are called MST solutions from the names of Mano, Suzuki, and Takasushi. These solutions can be used together with the post-Newtonian, because remember, we have to deal with all the multiples, okay, up to infinity, because we would like to resum fully the metric perturbations. The low multiples L equals 0 and 1 should be treated separately. But then there is the non-trivial task to sum first of all over M and then over L. The sum over L is diverging. This should be regularized somehow, removing the divergent part. When this is done, then one has the full reconstruction of the metric and can convert this information for what is really necessary, for instance, in effective one-body formalism, to deal with the problem of inspiring, for instance, of a system of two-body, analytically as much as possible. So as you see, this skeleton starts with the energy momentum of the test particle. So if you decide your particle is spinning, then there is an additional term. And there are complications due to the fact that instead of having a simple Dirac delta function, you have also the covariant derivative of Dirac delta function. If you want to consider the perturbation induced by an extended body having also quadrupolar structure, then you have second order in spin. That means second order covariant derivative in the source term, but the scheme remains more or less the same. In the Schwarzschild case, we are able to perform all these steps and get the final solution. This is tricky. The low multiples are available only in closed form, let's say, in the Kerr case. Partially in the Schwarzschild case. Partially in the Kerr case. And without this, we cannot complete the picture, because this is fundamental. And this is one of the main open problems, according to me, in the gravitational self-force formalism at the moment. So let me be more clear. Once you have computed the metric, it is not enough, but I was skipping this as a detail. You have to compute some gauge invariant quantity. This, and only this, can be used in effective one-body formalism, because we are working with a different system of coordinates and etc. But this has to be. So, briefly, what I told you now in detail. The cause of the perturbation is the first choice you have to perform, but then you have to put this energy momentum tensor at the right hand side of the Einstein equation, linearize in the perturbation, and write down the set of coupled equations. This is formal. Then you expand in spherical harmonics with all these coefficients which were introduced in the literature by Reggio Wheeler first and Zerilli after. These are spherical harmonic expansion, we know very well, but this is just to show the complications. For a generic orbit, geodesic orbit of the particle, the source terms are summarized by all these quantities involving the Dirac delta function. But when you specialize your orbit to be circular, the number of coefficients reduces very much, and what remains are only this, and only Dirac delta function at the position. Circular orbit means R equal constant position of the particle. So one can try to solve this system of equation working in a specific gauge. And the one I choose is the Reggio Wheeler gauge, in which several metric quantities can be set to 0. What remains are, as I told you, 3 partial differential equations in T and R for the odd part of the perturbation, and 7 coupled partial differential equations for the even part of the metric perturbation. Now, if one further makes the Fourier transform of the metric quantities, this coupled equations are no more partial differential equations, but ordinary, which is a big simplification. And for a particle moving along a circular orbit, the Fourier spectrum is very simple. It's only one frequency, this one. When the particle is not moving along a circular orbit, but there are eccentricity corrections, the number of frequencies modifies. And the modification is that if you are interested in eccentricity square corrections, then there are 3 frequencies. Eccentricity to the 4, which is the limit we have obtained up to now, this becomes 5 frequencies. So a discrete sum, and this can be done. When you rewrite the metric functions in terms of these odd new functions, the 3 equations collapse into one for what concerns the odd part. And this is, let's say, it's a lucky circumstance. And this is the Regge-Wheeler equation case. In the even part of the perturbation, something similar happened, but the transformation is a little bit more involved, and in the enter the Zerilli function and the derivative. But anyway, at the end, even in the case of the even perturbations, you have a single ordinary differential equation with some direct delta source terms. This is the Zerilli equation. As I anticipated, one can perform an additional transformation and reduce the Zerilli equation to the Regge-Wheeler. So what remains is a single equation to be solved perturbation. What does it mean? There are different source terms, but this is not relevant. We will solve this equation by computing the Green function. When you have the Green function, you have the solution. And we need now a pair of independent solutions of this second order ordinary differential equation. This one is the operator. What we do is to post-Newtonian expand the operator, and it means in powers of inverse speed of light, and then term by term add correction, including very high power in the inverse speed of light. But there is another important simplification which happens. In principle, you have to compute 2 different independent solutions, which is not the case. One is enough, because the other, what we call up solution, can be obtained from the first by simply replacing everywhere L by minus L minus 1. And this is expected, because in the equation, L is not appearing by himself, but only in this combination, which is invariant under this replacement. So, post-Newtonian solutions are computable, not by hands, with the help of the machine, of course. I'm using name. But let's give a look to the various coefficients in the powers of inverse speed of light. First appears L. What does it mean? It means that L equals 0 and this is okay. We will deal with the low multiples separately. But then at a certain order, theta to the 6, in the in solution there is in the denominator some L plus 2. That in the up case, when you put L into minus L minus 1, becomes 1 over L minus 1. So also L equal 1 cannot be used, and is minimum. Then we go beyond at eta 8, and then at eta 8 you find in the denominator of the in solution an L plus 3. That means in the up solution, this is L minus 2 in the denominator. So if you want to go beyond 1 over c to the 8 to the solution of your problem, this cannot be used. This post-Newtonian solution cannot be used beyond this value. Okay. Let's keep this. Imagine that I solve the problem of how to convert this post-Newtonian solution in some other pair of useful solutions. This is not in the literature even before all this approach was developed. Then you have the non-trivial task to sum over n, and this requires some hypergeometric function rules, but not only the functions, the Specola harmonics, but also the first derivative. And there are other summation rules required, which should be computed in advance involving the logarithms. Then you have to sum over L. Now, to sum over L, you have to really compute these things. Imagine that I would like to go at very high post-Newtonian level. So I can use the L equal 2 solution up to a certain low level, but I can replace the L equal 2 solution, which does not take into account the actual horizon of the Schwarzschild black hole, in terms of the what is called MST solutions. So take the multipolar L equal 2 solution and replace with the new one, which is regular and has no problem. And I can go beyond. But then it appears at -3. Then I need a new MST solution for L equal 3. It depends on how far I want to go. This solution, just to show here, can be given in terms of ON functions or in an infinite series of hypergeometric functions. This is technical. They show this kind of solution, they show an increasing transcendental structure because there appears pi, there appears Euler gamma, and there are logarithms. So, if I do this, I can reach the goal of summing. Now, in a moment, skipping the details, I will show the results. But it's clear that I have to compute several things in addition, in advance, and be ready to replace what I need as a result. The low multiple are the gauge information related to the fact that the particle is giving mass and angular momentum to the black hole, and this, in the Schwarzschild case, it's going on. And the regularization means to remove from the sum over all multiples what causes the perturbation to be divergent. This can be computed analytically in advance, or simply is a byproduct of writing down the series itself. So this is the example of the results of the contraction of the magnetic perturbation with the particles for velocity given in post-Newtonian space. So this is the 3pn, and then this was the new terms first computed in 2013. But then we were able to go beyond. However, in English one says let's call a spade a spade. So this technology was invented by Thibault and Moore radiations. The conversion of gravitational self-force information, this one, into EOB means that we are able to compute some potential, and this is what is done. And then in the gravitational self-force, one has computed a lot of elements. No time to go into details, but all the various potential and the effective one-body description of the two-body system can be computed in gravitational self-force theory up to very high order. First order in the mass ratio, the mass of the perturbing particle and the mass of the wave. So, after doing this, of course, we're computing several additional terms, like successive terms in the post-Newtonian series, so all the various potentials, this is what you cannot see. Let me mention only one tricky thing. I did this computation analytically. A colleague of us, a Vaisha, came into the game, and looking at this expression, it is one of the potential, said, but let's take 1 over r 10 to the minus 30. So this is a sort of binary code. So 10 to the minus 30, 10 to the minus 60, 10 to the... So yeah, 30 digits to understand the numbers. The coefficients of this expansion are unknown when you go very high with the expansion. And so, for instance, if one is able to compute with some hundreds of digits of precision this quantity,
then has a number of digits to identify the various coefficients. Remember, -1, +2, +5. And so if you know the structure of the terms you are looking for, there are algorithms, and he was using this, which allow to compute analytically from a numerical point of view, and this was a nice marriage between the two, the quantities we are really interested and we are interested for EOB representation. This is the algorithm. So we have tried to obtain information on this potential up to now, working with nickel. There are problems. These are the coefficients. The main difficulty is that then you are in the end of the machine, and at a certain point you have to put a number of flags to control what the machine is done, and this is the main difficulty for the moment. Main problem. Thanks for it.